Mm. Hello there, Jay. So, are you here for questions or are you here for the just the general walkthrough of the methods content?
Just
Hello?
the general content.
Yeah, sure. So it's just so methods 1, 2, you've probably just covered linear and quadratic equations, right?
Yep.
Two for your first 2 weeks. So this is just another PowerPoint, just goes through your general content. So you have your first up, you have your learning intentions, which is just essentially just to tell you about it. So warm-ups just generally, what is the gradient of 2y equals to 4x plus 6? And expand. You should all know how to do this, right?
Yep.
Yep. This is pretty clear. So we have the gradient is just in the form of y equals to mx plus c. So y equals to mx plus c. And then you want to turn it into the form. So for this one, you change it into y equals to 2x plus 3, and then your m would just be equals to 2. Pretty straightforward. And this expansion just go by our x plus, I think it was a plus b all squared equals, well, a minus b in this case all squared. It will become a squared minus 2ab plus b squared, the general rule. Now, so according to this, right, we would approach it the same. We have x and then we have 2ab. In this case, it's going to be 2 times 3 times x. So that's going to be minus 6x and then plus 9 in this case for this question. And then for your last but not the discriminant. Do you know what the discriminant is?
Yep.
Yeah, the discriminant, if you were familiar with the quadratic formula, you see the quadratic formula gives of x equals to negative b plus minus b squared minus 4ac on
Yep.
2a. Now, the discriminant is simply the thing inside the square root, so that's which is b squared minus 4ac. Now, if we were to find this discriminant of this following, well, equation right here, you could substitute the values in, and you get 16 minus 4 times 1, then times another 4, which what you get? Of course, right? You get 16 minus 16, which equals to 0. Now, knowing that the discriminant equals 0, what does that tell me? Do you know?
That is one solution.
Yes, if you were to equate this, which is this entire thing, like this gives you only one solution, right? And if you were to draw a graph up, if you were to draw a graph up that for example, if you were to draw a graph and you were to graph this equation out, you'd get eventually something that looks along the lines of this. You would only have one x-intercepts, right? Because there's only one solution to this discriminant. Well, the discriminant equals 0, so you only had one solution. Now, how does that work graphically? It's because that, you know how we have our quadratic formula, right? Given by negative b plus minus b squared minus 4ac on 2a. So our discriminant's inside the square root. So naturally, of course, right, if our discriminant equals 0, it means that no matter if you're plussing or minusing the square root, the discriminant, you'd still get only one solution because plus minus 0 doesn't change it. Now, think about it another way, right? If this is less than 0, what would you get inside the square root? You get let's say a negative number, right? Negative, let's say, dot, 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 whatever. That wouldn't give you a solution, at least no real solution. So that's what you must be careful of. So when they ask for you any solutions, you're gonna say there's no real solutions. If you dive into complex numbers, in which you would do, you're in specialist, then you would have solutions. Now, moving on. Oh, hello, Nat. Or is there anything that I can help you? Are you here for questions or for the general run through? If you don't really want to talk, you could just message me and I'll no. Now, we have our linear function, right? Good old pretty simple y equals to mx plus c, where your m is your gradient, your c is your y-intercept. That's your gradient intercept form, and this is the generally preferred form. If you were to do all your questions, I would recommend you put you define your function as mx plus c, because this is it's the best way in the sense that you have an idea where the y-intercept is, and you also have an idea of where the slope's going, if it's a negative sided or if it's a positive slope. And it's very easy for comparison. Now, you also have a standard form, which is ax plus by plus d. Now, this is useful in the sense that you could very easily find axis intercept, because if you let x equals to 0, you just simply get y equals to b over d, d over b. If you let y equals to 0, you get x equals to d over a. Quite simple, right? Now, moving on, there's just some other like finding equations. You have your formula. You technically just would get your gradients first, finding equations. You get your gradient first, which is given by y2 minus y1 on x2 minus x1. That's given just by your gradient. And then you'd simply just substitute it in and solve for in this case, this is a more easier way. And then you just substitute it into here and you get your answer. You get 3x minus 1. Now, this is one way, of course. You could also just go by y equals to mx plus 3. You find mx plus c. You find your y-intercept via having the gradient first, and then you just solve for c, which is also a viable option. Now, moving on, parallel and perpendicular lines. Did you guys cover this yet? In the sense that, what's the difference between them? Parallel.
Yeah.
Yeah, so you generally, if you have two linear lines, right, the only relationship between them is either they are parallel, so they're parallel, right? Non-parallel, which then gives non-parallel, my bad, non-parallel, which then gives you the outcome of either being perpendicular or just normal. Now, or just like normal. Now, looking at parallel lines, right? There's two cases, because there will be questions asked in the sense that later on is like for what values of, let's say, m or some particular number would these two lines intersect forever or intersect? If I give you the example, so I have y equals 3x plus, let's say, k, and I have y equals to, let's say, for example, kx plus, I don't know, kx plus what, 4. Now here's a question: for what value for these two, what values of k do they intersect? None. This is the type of VCE questions that would come up, and it's like and you need to deal with the idea concept of understanding that, okay, if they are parallel, then they either they are the same line, and it says looks like this, or two, they are different lines, which looks like this. And therefore they don't intersect. Now, if we want to meet the condition of them being a parallel line, of course, our gradients must be the same. So you get the idea that k equals to 3. And now, with condition k equals to 3, they're not the same line, because now I have y equals to 3x plus 3, and I have y equals to 3x plus 4. They are two completely different lines, and therefore that would make sense. Now, coming back to parallel and perpendicular lines, it's just a way to say that, okay, if you have two lines, how do you prove that they're perpendicular? You just have to say that the gradients, when multiplied, gives you -1. In the sense that maybe this is 3, so this has to be -1 on 3. Just simply that. That's just simply it. Now, if a line, for example, right, if a line A has gradient 2, another perpendicular line would have a gradient of -1 or 2. Now, methods of solving equations. Now, this is for quadratics, because solving linear is quite easy. For quadratics, right, you have two ways. You have three ways, technically. Oh, my bad. Let me just remove that. Chuck that back up. You have three ways, technically. First and second way is you go by factorization. One is performed through just using your normal factorizing. You look for factors of this, your constant, that adds to your coefficient of x. You also have second, which is you complete the square, which is you just, in this case, you go x minus 5 on 2, whole square, then minus 25 on 4, then plus 6. And that's just simply it in a sense that this is your complete square. And why is this useful? Because you get it in your turning point form. This would eventually give you minus 9 on 4. Get your turning point, right? You know that your turning point is going to be at 5 on 2, and then with a y-coordinate of negative 9 on 4. This is your t dot p. Have you learned about turning point yet? Or turning point form?
Yeah.
Yeah, so completing the square puts it in turning point form for you. And it's very easy when you graph it, because you could just, when you start graphing it, you just get 5 on 2 and negative 9 on 4. And you could just immediately begin drawing what it looks like. And that's why it's useful. Now, you also have your last, but not least. It's the most standard way of finding your factors is you go by your quadratic formula. Quadratic formula technically works as a brute force. It puts everything into just solving your two factors, and eventually you would get x equals to whatever. So, and then that's your way. This is only doable if you have an equals to 0 on the other side. If there's no equals to 0 on the other side, you can't perform the quadratic formula. Does that make sense?
Yeah.
Yeah. These are all pretty basic stuff that we covered, right?
Yeah.
Yeah. And then you have your discriminant, etc., just your different values.
Mm.
And now this is your polynomial, factorized position, turning point. And then now sketching, right? There's a couple of stuff that I need to talk about, in the sense that sketching is important because on the exam, you'll be marked on your sketches. And there's generally goes for, you have your axis intercept. This is a must. Asymptotes, if any. These are all must. And then now what comes next are turning points. You must label all of them. And then last is just your shape, general shape. So when the examiner takes a look at your graph, that's what they're going to look for. All your axis intercept must be labeled, all your asymptotes must be labeled, any turning points must also be labeled, and last of all, your shape, general shape of your graph. This is the 4 points that they will take a look. Of course, you need to label your axes well, but that's default, right? So for the example with this question here, right? Of course, we need to show all key features. So I need to look for, there's not going to be any asymptotes, right? Pretty simple. But we're going to look for our axis intercept. And first of all, we got to look for y, because it's the easiest. In this form, I'll just let x equals to 0, and I immediately get y equals to 5, because that's the only constant. Now, what comes up next is you're looking for the x-intercept, and that requires you to factorize it, and you eventually get the points 1, 0 and 5, 0. Now, this is why the turning point formula or completing the square is useful, is because that you can use it to find your turning point. For example, right, y equals to x squared minus 6x. In this case, our equation, I use a completing the square, I get x minus 3 all squared minus 9 plus 5. I just get minus 4. So that puts it in a very simple and direct that you could visualize, oh, the turning point is going to be at 3, -4. And then you have your point, and then you can immediately start storing it. So you have 0, 5, you got 1, 0, you got 5, 0, and you got 3, -4. And there you go. That's your full graph. Of course, you've got to include your y and x. So this is what an examiner would look for. Well, in your exams, right? So work examples, sketching. Your axis intercept, your labels, and then your asymptotes, turning points, and your general shape. Think of it as a checklist. Are you in year 9 or are you in
11.
year 11? Oh yeah, my bad. Yeah, year 11. Yeah, so you guys should be pretty familiar with this. Now, transformations. Have you guys covered transformations yet a bit?
Just a little bit.
So, this is where it comes interesting. So give me a moment. I'm gonna stop screen share and I'm gonna open up Desmos. This is where transformation comes interesting.com/calculator. Now, why do I say it's interesting is because this would be a very great way for you to visualize it. So you see we have our thing, right? Our shape of the graph is either going to be in two forms. Y equals to ax squared plus bx plus c. That's one. I would also have something else, which is technically looks a little bit better, is that if I want to consider the idea of dilations transformations, you must put it in turning point form. Now, what I mean by putting it in turning point form is that if I have, let's say, in turning point form, everything will become significantly easier. What do I mean by that? All right, so let's take a look, right? Let's ignore that one for now, and let's take a look at our turning point form. I have, let me just move this a bit. I have these items, right? I got my A, I got my H, and I got my K, because that's your turning point form. What happens when I decide to move A around? Let's say if I decide to make it bigger, what do you see is happening? What's happening? Um, if I decide to make A bigger, what do you see is happening to the graph?
It's getting smaller.
It's not getting smaller, it's getting what? You're becoming thinner, right? So you're
Yep.
kind of compressing the graph. If you look at what my hands are doing, kind of compressing the graph inwards. Do you see?
Yep.
So, and now let's take a look. Imagine if I just ignore this for now, right? I put it back to 0. Now, what happens when A gets smaller? You can see that the graph is becoming stretched, right?
Yep.
Now, how does this work in the sense that, oh, a dilation? So you can think about it like this. A dilation from a dilation, let's say for 2, right? From the y-axis, it means that you're stretching it from the y-axis. Do you see what I mean here? You're stretching
Yep.
it. A dilation of 2 means I'm stretching it from the y-axis, which means that, so my original graph, right, it's y equals to x squared. Let me just put that in. It's y equals to x squared, right?
Yep.
Now that I've stretched it, let's say for this point here, right, I originally had, I would assume here it's 1, 1. I originally had 1, 1 at this point, right? Y equals to x squared. Now that I've stretched it, what happened to the y value? It went from
Um,
1. At the same x value, I have, let's say x equals to 1. At the same x value, originally I had 1, 1. But now I only have 1, 0 point, what?
5.
0.5, which means that, all right, so when I stretch it by 2, technically what happens to my x value is that for every single point of my x value, my y value has went down by half, right? It's been half, technically. you'd see that this works for everything, right? I could have it for, let's say, 3. I can make it smaller. 2. You realize that at this point it's 2, 2, and this point it's 2, 4. So this is what dilation is about. When you're stretching on the y-axis, what you're doing is that you're doing something to the x. Now, what are we doing? Here comes the more fun part. What are we doing to the x? So if I have, let's say I have my function, right? Y equals to f of x. Familiar with this notation?
Yeah.
Should be f of x, function of x.
Yeah.
Yeah, familiar with this notation. Good. Y equals to f of x, which is the same as, let's say I call it x squared, right? Now, what happens when I decide to, let's say I change x to x on 2? I'll just tell you this. So this is a dilation of a d to y, which means that I'm dilating 2 from y-axis, which means I'm stretching it. Now, what will this do to x is that it will half x. Why is that? Because, right, if I just decide to stretch it, for every single x I have now, it's being halved. And if I decide to write the graph out, I decide to substitute this in, right? X now becomes x on 2. I have y equals to f of x on 2. Now tell me, if it's x on 2 here, what becomes of this?
Um,
You know that if I have y equals to f of x, right,
yep.
which equals to x squared, and I decide to do f of 2, what happens? I'm replacing x with what?
2.
So I become 2 squared, right? It's the same
Yep.
thing here. I replace my x with what?
Um, X on 2.
Good, and I get myself x on 2 all squared, which when I expand it becomes what?
Um, oh, sorry. What was the question?
When I expand it, what does it become?
2x, 2x on 4.
2x on 4? What are we doing? We're x on 2 times x on 2. That's not going to give you
Uh,
2x.
um,
Top with top, you get what?
X squared.
Good, and then bottom with bottom, you just get x squared on 4, right?
Yep.
Now that's what when you mean. That's what I mean, your dilation from 2. Okay, so if I decide to change it a bit, right? I have x squared, and now I have, let's say, 1 on 4, 1 on 4, x squared. Interesting, right? I originally I had my value at 1, 1, right? Now it's being stretched out, and now I have 2, 1. Do you see this?
Yep.
So this is what I mean by stretching from the y-axis, because when you do, let's say, when you stretch by 2 from the y-axis, you're doing the reciprocal of what's happening to your x value. So if you have, let's say, f of x, right? You just do the reciprocal, which is divide by 2. So you have x on 2, and then and then you realize that, oh, what does that do to my graph? It makes it stretched out. And this works for everything, right? You take a look at even here, you have 2, 4. In this case, it'll be 4, 4. Exactly double. Does that make sense?
Yep.
And that's what's mean by your dilating. Now, what about translating? It's quite similar, right? Imagine now that you have, let's say, imagine now that you have what? That you have, let's say, this graph again. The easiest part is moving up and down. How would I move something up and down?
You change the y.
Yeah, you just add something to it, right? I could get y plus, if I originally have y equals to x squared, right?
Yep.
If I added 1 to y, what would happen? I'll get what? X squared plus 1. Now, what does that look like on the graph? It looks like this. You see? It's being moved, what? Upwards, right?
Yep.
This is being moved up to here. And if I have, in this case, it will be 1, 1. It's being moved up to 1, 2. Now, what happens if I decide to do minus? Oh, it's being moved down, right? So that it's quite
Yeah.
clear, moving up and down, it's simply just whatever function you have. For example, y equals to f of x, right? Which equals to, it could be whatever, just give me some random numbers, right? Like that. If I decide to do f of x plus 2, which means that I'm adding 2 to the entire thing. What's going to happen in the graph? We'll see. I have x squared plus 3x plus 1. Right? Now, if I added 2, f of x plus 2, can you tell me what f of x plus 2 would be?
Um, 4.
F of x plus 2. So you're just adding 2 on at the end. What's f of x? The entire thing here, right?
Yep.
That's f of x. So if I'm going
Um,
to do x of x plus 2, I would just get y equals to what?
x squared.
Plus
3x
3x
plus
plus
2.
1, then plus 2, which is plus 3, right? And what does that look like when we graph it? Here comes the magic. What do you see about it? Is that, okay, I have, at any given point, my new graph, right, the blue one, is 2 taller than the green one, right, my original graph. You could even take a look at here. It's exactly 2. Now, that's just your translation, right? You're moving it up and you're moving it down. Does that make sense? So if you have your function, right, your starting function, let's say f of x, if you want it moving up and down, you simply just do f of x plus 2 minus 1, etc. I could even go on and I change that a little bit. If I decide to imagine it as minus 2, then it will be minus 1. It'll become 2 units smaller. Now, this is only just going to be a brief introduction of you to you on the idea of dilations and translations. It'll become more evident when you get on later on, because this is, I think, this is term 2 content. Now, moving back to the PowerPoint. So, linear quadratic system. Have you ever came across a question in which it asks you how many points of intersection does a linear line have with a quadratic line? Have you came across those questions before?
Yeah.
Yes, and your way of solving them is just simply you equate them, right? So, for example, y equals to 3x plus 1, and I have y equals to x squared plus 4x plus 4. Your best way to go is just simply equate them and you solve them. I have 3x plus 1 equals to x squared plus 4x plus 4. Equating it, I'd eventually get to x squared plus x plus 3. And then you just go by either your quadratic formula or you complete the square. In this case, you won't get any solutions. Why? Can you tell me?
Um,
Will you get a solution?
1. No.
No, right? Why?
Because it equals 0.
What equals 0? Nothing equals 0 here. See, when we have a quadratic expression, right, and it equals 0, my first question is to think, does it have a solution?
2.
Does it have a solution? So we got to check, right? And what's the way of checking if there's a solution or not? We use a what?
All factor law.
Uh, no, no, not the no factor law. It has something to do with we covered here. It's the what? The triangle thing, right? What do you call it?
Discriminant.
Yes, and discriminant is b squared minus 4ac. Now let's take a look at b squared minus 4ac, right? What's b?
X.
Remember what's b? b, a, b, c. They are the coefficients, right? They're not. So what's the coefficient of x?
1.
Good, so I have 1 squared. And then 4ac, I have 4 times 1. What's the coefficient of x squared?
1.
What about c?
3.
Good, right? I get what? 1 minus 12. So what do I know about the discriminant? It's what? It's less than 0, right?
Yep.
When the discriminant is less than 0, what do we know?
There's 2 solution.
Nope, the other way around. Other way around. When the discriminant is less than 0, there is no solution, right? So
Yep.
here's how the table would go. You have your discriminant less than 0, which is no solution. Discriminant equals 0, you have 1 solution. And discriminant bigger than 0, you have 2 solutions. Does that make sense?
Yep.
Now, since this is less than 0, it has no solution, right? So we won't have, let's say, a point of intersection. For the question here, the question that they gave, right? I have 2x and I have x squared minus 3. If I decide to equate them, I'll get 0 equals x squared minus 2x minus 3. And I could take a look at the discriminant, right? A discriminant would be negative 2 squared minus 4 times 1 times negative 3. I'll get myself 4 plus 12, which equals to 16. So that is a positive number, right? So discriminant is bigger than 0, so 2 solution. My goal is to find a 2 solution in which I just factorize it. I get x minus 3 and x plus 1 equals 0. And by the null factor law, I could have x equals to negative 1 and 3. Does that make sense now?
Yep.
Yeah, and that's now linear quadratic. You've done these questions before, right? You could also do quadratic and quadratic. How does that work? For example, right, I have x squared plus 6x plus, let's say, 4. And I have the second equation, I have maybe 3x squared plus 2x plus 7. Right? Two graphs that look completely unrelated. If I were to find how many points of intersection, right? What would I do? It's the same thing, right? I would equate them together. Now, equating them, I will have x squared plus 6x plus 4 would equals to 3x squared plus 2x plus 7, right? Now, my goal is to make one side 0, right? So I could then apply either the quadratic or just take a look at my discriminant. Moving them to the same side, I would have 0 equals to 2x squared minus 4x then plus 3. Now, if I look at my discriminant, I'll get discriminant equals to 16 minus 4 times 2 times 3. I'll get 16 minus 8 times 3, right? Which is 16 minus 24. This would be -8, which is what? Less than 0, right? Now, the discriminant is less than 0, so what can you tell me about this?
There's no solutions.
Which means that the two graphs does not have a point of intersection. And now let's see it in action. Just refresh this. Leave. And my first graph, x squared plus 6x plus 4, looks like this. And I have my second graph, 3x squared plus 2x plus 7. Now, you see? Is there a point of intersection? No. It barely misses it. So that's why we have our thing, which is my equation, and that's less than 0, which means that the two quadratics never touched. And if I were to change this up a bit, maybe I put it down to 3, I would get something, right? I would get 2 points of intersection. And then if I change it back down, if I put 3 instead of the 7 over here, I would get the same thing. Yeah, I would have a discriminant which is positive. Does that make sense?
Yep.
Yeah. So how's this sounding so far? Is it complicated or are you feeling all right?
Okay.
Yeah. So same thing with here, right? Now we understand a little bit of the quadratic solving, looking at the intersections between graphs. We have our tangents and discriminant. How does this work? Is that if I were given maybe a particular thing, let's say y equals to kx, right? I don't know what the gradient of the graph is, but I want to look for a particular gradient in which that when I intersect it with a parabola, I only intersect it once. Now, what does that look like? Is that, imagine I have what? X squared plus 4, right? This is a parabola. What would a line look like if it intersected once? Is that if it's just like this, right? Touches it once. Now, it's pretty much the same thing. I want to create a case in which that if I want to look for the number of intersection point, I need to look for the discriminant, right? So I would find the intersection point first, which is by equating the two equations. I get kx equals to x squared plus 4. What's my next step? I need to make sure one side equals to 0, right? I get 0 equals to x squared minus kx plus 4. Now what do I have? I have a quadratic expression, right? And I could look for the number of solutions by looking at the discriminant. And can you tell me what's the discriminant for this one?
Um,
What's the coefficient of x?
1.
Is it 1? If you look at here, is it 1?
Negative.
Negative what? What's that other in front?
Okay.
Negative k, right? So I get negative k squared. And what's my 4ac? What's my a? What's my c?
1 and 4.
Good, right? So I'd eventually get what? When I square negative k, I have what?
2k.
You sure? 2k? Negative k times negative k.
Just k squared.
Good, k squared, right? And then I have minus 4 times 1 times 4, which is minus what?
Negative 16.
Yeah, good. So I have my discriminant is now no longer a number, right? It is a what? It's an equation in terms of k. So technically, if I wanted, I could change my values of k to change my discriminant. What does the question ask me? What values of k does the thing have intersect exactly what? Exactly once, right?
Yep.
So what do I need my discriminant to be?
0.
0. So if I equate this to 0, I get the equation what? K squared equals to,
16.
yep. So what would k be?
4.
Yep. And just a note, we also have -4, right? Because -4 squared is also 16.
Yep.
And that's it, right? And how does this look in place? That means that the line y equals to -4x and the line y equals to 4x will touch the parabola exactly once. What does that look like? It's simply that if I have what? -4x, right? And I have x squared plus 4. It touches it exactly once. Do you see it?
Yep.
And I have 4x as well, which is on the other side, which also touches it exactly once. Does that make sense?
Yes.
And now if I want to, now what happens if I want two solutions? Can you tell me? What do I need my discriminant to be?
Higher than 0.
So in this case, I would change it so that I have k squared minus 16 would be bigger than 0, which means that k squared must be what?
+4.
Well, no, k squared. Just move the 16 and get round, right? I have what? K squared must be now bigger than what?
16.
Yep. K squared must be bigger than 16. So anything that's either what? Less than -4 or bigger than +4 would work, right? Because anything less than -4, what would happen? I would have, let's say, -5, right? What's -5 squared?
25.
Good, right? Anything, same with -6, right? So anything less than -4 would work, and anything bigger than -4 would also work. Right? And how does that put into play over here? Is that I could imagine if out here I put -5. How many times does that intersect it? You have one time here, and you have another time here. So your discriminant tells you how many intersection points there are. Does that make sense now?
Yep.
And then because you have a variable instead of a number, because you have k, you could change k around to have the wanted amount of intersection points. And that's the idea of this question would most likely be on maybe your year 12, maybe your year 11, maybe some of your tests. That's a good question. So it's the same thing, right? I have an exit ticket problem. You could do it. You could try to do it. You could not. Don't try to do it. You could give this a try. Exit ticket problem. It's just a parabola. And after that, if you have, yeah, just if
Yep.
you get the equation, give it a try. And after that, it's just Q&A.
Okay.
So if you have any questions, feel free to ask. If not, you could go off, do your own stuff, or yes, or you could like keep hanging around and see if there's any other people who's around here. Maybe they would ask questions as well, but yes. Now tell me once you have an answer, and then I'll go through the run through. I'll go through the walkthrough.
Um, Y equals x minus 2 squared plus 3.
X minus 2 squared plus 3. All right, so let's take a look, right? So let's first try if I have it. Yep, because you have your turning point form. Good. But then what's the other requirement? It must pass through 0, 7, right? So let's
Yeah.
check if it works. So I have, normally I have an A here and I want to look for A, right? I have 7 equals to A and I get um negative 2 squared plus 3. And I have 7 equals to 4A plus 3. I get 4 equals 4A and A equals to 1. So good. It's just simply y equals to x minus 2 all squared plus 3. And this is the type of question that you would have in your you did at school, right? Or at QS.
Yes.
Yeah, quite similar, right? And it's not that hard, it's just a rough idea. The hard part about this is that you understanding how the discriminant works. Right? So remember the table, right? If your discriminant is less than 0, you'd have no solutions. Equals 0, you get one answer. And if it's bigger than 0, you'd have two answers. It also works for intersection. Does that make sense?
Yep.
Yep, and that should be it. Do you have any other questions? Maybe some advice? You want some advice about methods? You want some advice about special or something else?
Um, yeah, maybe some advice about methods.
Do you do special, by the way? I just asking.
No.
No. Okay, so methods, right? Methods in comparison to special, methods is a very English heavy math subject. Now, what do I mean by English heavy math subject is that it is very focused on the idea of you are able to interpret the question correctly and quickly. So let's say a particular methods question, right? Special questions are straightforward in the sense that you need the formula itself is already hard to figure out. So they're not going to trick you up or try to make you lose marks on the question itself. But methods is different because you have a very large group of people who do methods, right? Think of your friends. Some of them, perhaps they're not that good at maths, but they're still doing methods, right?
Yes.
And you also have those friends who are exceptionally good at math, but they're also doing methods. So how are they gonna distinguish between the very good and maybe the good but not the toppest? How are they gonna distinguish it? Of course, make hard a little bit uh they make hard a little bit twisted, if you would say, questions to try to stop some people, right? So your methods, my tip is to read carefully and get used to doing questions so that your mechanical calculations will become natural to you. And the only thing that you need to think about is finding ways to solve the question. Does that make sense? Now, do
Yep.
you get what I mean in this case? So
Yep.
it's like having you want to practice yourself so that later on when you get into derivatives, the derivatives becomes natural. Everything calculation wise, let's say maybe some powers, something squared, anything calculation wise, like finding the discriminant becomes a natural and it's like a one click moment. You immediately get it and you could do the question.
Yep.
That's what I mean by your mechanical thoughts being a natural, a very quick one. But then you want to also do enough questions or have a broad view, let's say, broad practice of questions so that you could maybe when you have questions, when you get into very strange ones, because that's where they try to trick you up, is that so those type of questions you would want to, because you've done enough, you have a large pool of questions that you've done, you could think of something similar and you could try to use that to your advantage. Do you get what
Yep.
I'm saying? It's a little bit convoluted.
Yeah.
Yeah. So methods is it's a math that is English heavy. You need to make sure that you read your questions carefully. And then you need to also look at the question itself and try to think of ways to do it quicker or to do it in a way that the examiner wants to. Because rather than Spesh, which is just simply just some calculations, methods, they will give you a slab of text. I could show you some, let's say, past methods paper. So VCE, let's say, methods 2025 exam 2. Let's put that in. You can take a look at it, right? So you have your math exams 2. See, you have a slab of text. And then they want you to do it. If you move further on in the worded question, right? They give you a slab of something and then they ask you to do it. It's much cleaner on the final exam, but for your SACs, it'll be very, very, I would say, convoluting.
Yep.
Because your school also wants to know who does good, who doesn't do good. So yeah. So that's what school do you go to, by the way? Just out of curiosity.
So high.
Pardon? Q High?
Boxer.
Oh, Box Hill. Box Hill High. Ah, okay. Fair enough. I do have some friends who I know from Box Hill. I thought you said it's
Yep.
large group. So it's just that you want to know how to do this, right? Methods is just practice makes perfect.
Yep.
You do enough questions, you'll be able to get all the basic marks. And then that would guarantee you probably you've got all the basic marks. That would give you like about 37 to begin with. And then the more
Okay.
you do, the more you're able to secure yourself the higher marks, which you gradually push you towards a higher end of the A plus.
Yep.
Do you know how VC study scores work?
Kind of.
Kind of. So I'll just give you a brief overview, right? Study scores, they are based on your ranking, right? How you perform compared to everybody else. You know that, right?
Yes.
So you have what your final study score comprised of, what's compare you to other people is technically you have your SACs, right? And then you have your final exam. Now, if you want a 37 plus study score, right? On your final exam, you must at least have I remember, I think it was A's for your final exam. So your exam 1, exam 2, and at least right, A's throughout your SACs. Perhaps maybe 1 A plus.
Yep.
Does that make sense?
Yes.
And then if you want, let's say, a study score of 40 plus, then that's where you get into the concept that you want to have your A plus, A plus, A plus, A plus. This would get you like a borderline on the lower end of the A plus would give you a 40 plus. Anything above that, you're going in for the higher end of the A plus, middle to higher end. So 45 plus is you want the higher end of A plus, which is technically means you want at least a 95% on everything.
Yeah.
Now for your school SACs, right? It can be a little bit easier. You don't need to worry about too much because school SACs is based on your ranking at school, and then that can shift up and down depending on how everyone else in the school. Right? Oh, hi, Philip. So yeah,
Hello.
uh, so yeah, Jay, that's pretty much what all you have to worry about. Just for methods, my tip is that just practice. Not practice makes perfect. Oh, Philip, do you have any questions?
Yeah.
Yeah, feel free to ask.
Um, uh, can I like read the question out? Because this one's kind of hard to send.
Sure, I'll open up a whiteboard. Give me a moment, and then where's my whiteboard button? Okay, new whiteboard. Here we go. Yes, yes, yes. Let's get it. Let's get it started then.
Yeah.
Yep. So what do we?
So it's a composite function question. So it's like
Mm-hmm.
let the inner function, which is gx, be x squared minus kx plus 5.
Yeah, I'll
And
write that x squared minus kx plus 5.
yeah, and then it's already known that fx has the roots at -2, 1, and 4.
Negative 2,
Mm.
1, and 4. So that's
Yep,
fx, right?
fx. And then we ask um what like states the value of k such that f of gx equals 0 gives the maximum number of solution possible. So, with this question, like I know how to approach it. It's just when it comes to selecting the answer, I'm not quite sure like how.
So in this case,
Yeah.
fx, did they tell you it's a third degree polynomial?
Um, I think it's just a cubic. It's just a cubic. It should
All
be just,
right, because that's quite important.
it
That
should
is quite important.
it should be just a cubic.
So it's asking that what they're asking is that the maximum number, what value should k be so that it guarantees a maximum number of solutions, right?
Yeah.
All right, so that's something interesting, right? Because what let's take a look at these in each individual ones per thing, because the number of solutions, right, really depends on how many is in here, how many is in here, and how many is in here, right?
Yeah.
So if I take a look at x squared minus kx, then I instead of plus 5, I go plus 7. That's a
Yeah.
plus x plus 2. I have x squared minus kx, I have plus 4. And I have lastly x squared minus kx, then plus 1. Now
Yeah.
let's take a look at
Mhm.
where the discriminants are at for all of this, right? And what we want is we want to find a number value for k that which all the discriminant is bigger than 0.
Oh, yeah. So you want to find like a discriminant which like covers all of them, like the biggest range one. And
So
then
let's take a look at our first one, right? What's our discriminant? It's going to be k squared
minus
minus
20,
28, right?
yeah,
Second one will be k
k
squared.
squared minus 16,
Good. And the last one will be
and then k squared minus 1.
minus
Oh,
1. Now let's take a look at these discriminants, right? If I just want a value for k that I want this to be bigger than 0, I want this to be bigger than 0, I want this to be bigger than 0. So, when we have a quadratic and we have a quadratic inequality, we want to solve it. What do? We must draw out the quadratic, right? And it says that it looks like this, and it looks like this. Do you see my screen?
yeah,
Yeah, these, right? And this part would be here would be root 28 negative, right? And this would be
yeah,
positive root 28. This would be negative 4, 4, and this would be negative 1, 1. Now, what we want is we bigger than 0, right? So both this. But what do we realize about this is that what? The 4, this discriminant and this discriminant, right? The negative 4 and the negative 1, they're all kind of like in here. You could all combine them into one.
yeah. And then is the reason why we use greater than and not greater than equal to is because we're trying to find the like
Maximum.
maximum number of solutions. So we always want like two solutions.
We want to look for where it has two solutions, right? Because
Yeah,
maximum, right? Now we have something, right? I have, as long as it meets the criteria for this thing over here, it meets also meet the criteria for the rest, right? Because we combine all the quadratics into a one little, let's say, graphish thingy. Number line thingy here, we realize that, oh, if it's bigger than if it's bigger than root 28, then it's of course bigger than 4. If it's bigger, which is of course bigger than 1. If it's less
yeah,
than negative root 28, it's of course less than negative 4, and it's of course less than negative 1. So it
yeah,
follows that as long as this criteria is met, I would always have two solutions for the remaining two.
yeah, yeah. Makes sense.
Yeah, and that would give you, if you have strictly bigger than the root 28 thing, you would have minimum number of 6 solutions. You would have 6 solutions,
Yeah,
right? No matter what.
yeah. So yeah. So approaching this question, you would Like first you see that f of gx equals 0. So that's basically when the function is like when all of the roots like it's matching to all of its roots. So you want to just plug the gx function for the x and then solve when that's equal
Yes,
to 0. But
yes. Each separately because we're looking for the maximum number of roots, right?
yeah,
Yes, you just look for each individual root because when you plug that quadratic in, right? What you're doing is that you're turning it from a linear factor, right, to a quadratic factor.
yeah.
And because you're adding that extra degree in, you
Have
may be able to create an extra root. So that's
yeah.
what they want you to think
So
by
that's
creating that extra root.
so then there would be a maximum of 6 solutions possible.
Yes.
Yeah.
It depends on the value for k. And really depends on what actually g of x looks like. So in this case, they gave you a quite good looking g of x. If they slightly change it around, right, and they're not completely, let's say, covered, you might face up with the criteria. You might end up with the complication of, okay, what? You see we had that thing in which that they're all like within a loop, right? They can be all inside the big one.
Yeah.
If they were to make this question difficult, they could be do something like along the lines of this.
Oh. And
So
then
then
you
you
have
would have to
yeah,
apply, right? The maximum number of roots.
would be past this point, but then with the other side, you also have to make it past this point, which is a different route.
Yes. Right.
Yeah.
That's a way to think about it. Or maybe if they ask you for one root, well, that is okay. Well, you have one root. Well, now that's a very interesting one, right?
Yeah. So then you wanted to equal to 0 instead of greater than 0.
Yeah,
Mhm.
not just one
Oh.
one root. So for some of them, you have to have a less than zero.
Oh, yeah. Wait, for like one root in general, like for the
In
whole.
all for a
Oh,
whole
yeah,
thing.
yeah, yeah. So then
That's
you have
how they make the question significantly more difficult, right?
yeah. So then you would have to consider all cases. For example, if the first one you make the first one equal to 0, then the rest of them have to be less than equal to 0. And then you
Yeah.
consider like 3 different scenarios.
Yes. Right. So that's also one way to think about it. So
Yeah.
that's how they can make a question like this significantly more difficult. But I guess they're trying to introduce you to the idea of getting the number of roots and what the factors. So
Yeah.
it's not going to be that difficult.
Yeah. Be fine. Yep.
Does that make sense?
Yep, that makes sense.
Is there any other questions like that you've got? Wait, you're starting year 11, right? What, year 12 or year 11?
Year 11. So three, four methods.
Ah, right. Have fun, have fun.
Yeah.
Have you started doing the content ahead? You
Yeah,
better.
yeah, yeah. So over the holidays, I've been looking through like both of the integration things, so like
Those
indefinite,
area of study
definite,
too.
and also what do you call it? Integration by recognition.
Yep, that's
And
nice.
then
Good start.
also I think I've learned most of probability. I think I just need a few like practice questions for them until I like
Probability
yeah.
is actually the easiest for the methods. Actually, the easiest
Yeah,
subject.
I think I think it was just like in terms of understanding, but once you understand it, you just have to apply the simple rules and then you get them.
Yes, you've got to know how to use sarcasm.
Yeah.
That's the thing about probability. You got to know how to use sarcasm. You must know how to use sarcasm. Otherwise, you can't do stuff
Yeah.
on probability because it's very, very cast heavy.
Yeah. I think the hardest one in there would probably be the confidence interval. I think that one like conceptually is the hardest one to like grasp, but
You
like
understand it? If you don't understand, if you're still a bit iffy out about it, I can still give you a quick run through about the confidence interval, how that works.
um yeah, yes please.
Yeah, so confidence intervals, right? Generally, right? Confidence interval is something that you would do in the sense that you only have a proportion, right? You don't have a proportion. You know your proportion, but you don't know something about the larger population, right?
Yeah. Yeah.
So how does that work? Is that the confidence interval, they are derived from something what we call, oh God, that's very thin. That looks so much better. Now, it's derived from something what we call the confidence interval. It's derived from something what we call the central limit theorem. Do you know what that is?
Central limit theorem.
Central limit.
Is it the one where like you draw like a straight line and that's the population and then you have like 20 different samples and then one of them is like outside and then like if you want 95% confidence.
So here's how we go. Central limit theorem and the law of large numbers. Your confidence interval, right? It's based on in VCE, you only come in contact with either binomial distribution
Yeah.
or normal distribution, right?
Yeah.
So let's talk about how this works, right? Binomial distribution, it makes sense, right? That if you have, let's say, a large number of binomial distribution, right? You not just once, not just twice, you have, let's say, tossing a coin, right? You either have heads or tails, right? And let's call this graph the number of heads, right? In, let's say, 10,000. Does this make sense? Yeah,
Yeah.
of course, your center is going to be at what? 5,000, right? That's going to be your center. That's going to be most likely where the most number of heads going to occur, right?
Yeah.
But then, right, of course, you're going to have lesser numbers, right, as it go out, lesser numbers as it becomes lesser, right? Less probability.
Yeah.
Now, the central limit theorem, it says that given there's enough binomial distribution, right? Given there's enough tosses, there's enough throws, you're going to eventually come with, you're going to eventually, for your binomial, right? You're going to eventually have the idea that it's going to become normally distributed.
Yeah.
And that's why for binomial, right? If you want to do a confidence interval test on binomial, you're instead of having root n, you just simply have n. Does that make sense?
Yeah. But for the binomial bit,
Yeah.
is it like at the start, is it like is it a different number of trials or is it like the same number of trials but just at the start it's different?
What do you mean?
Um, is the end bit like 10,000 in terms of like you're
Yeah,
rolling
just 10,000 number
10,000
of heads. So
or
each of
10,000
this,
number
right?
of heads? Yeah.
So each of this means that I performed a 10,000 number of heads. I performed 10,000 tosses, right?
Mhm.
And each of this line means that maybe maybe each of these line it means that, oh, I maybe perhaps performed this thing like a million times. And this is the distribution spread.
Yeah.
So of course, right, your large number of binomial distribution. So maybe how does this work? Maybe in one try I got 5,000, right? 5,000 head, 5,000 tails. Then it's gonna be spot middle. It adds one to it.
Yeah.
If another try I got a 5,000 again, it adds another one to it, and therefore the line builds up.
Yeah.
Does that make sense now?
Yeah. So if you do it over and over again, the possibility of like you getting like 50-50 would be the largest, which is in the middle.
Yes. And then this follows what you call a normal distribution because as your number of tries goes from a million to 10 mil to 100 mil, right? As it goes into infinity, theoretically, by the central limit theorem, you get a normal distribution with the mean at 5,000, which is NP. You know what NP is, right?
Yep. Yep.
Number of trials times the possibility.
Yep.
And your variance would be, tell me, what do you know? Have a guess?
Variance should be variance. Isn't wait variance. Isn't variance the EX squared minus EXO squared?
Yes,
Which is with
but you're not going to be able to find it using this. You're not going to be able to find it using this, by the way. I'm just telling you that. You, you can search it up if you want. It's much better if you search it up. You find it out yourself. So search up what is the variance of a binomial distribution approximated. What is the variance of a binomial distribution approximated using a norm?
So uh, MP times 1 minus P.
Good, right? MP times 1 minus P.
Yeah.
And then this is of the basis of your confidence interval, right? That's where you would build your confidence interval from.
Yeah.
So this is a binomial. Now, normal-wise, right? Normal is quite simple. You just have your P. Yeah, you're giving your population proportion, right? That should be your mean in this case.
Yeah.
Population
And
proportion, let's say out of 40%. It's 40%, right?
yeah.
And then they'll probably give you maybe a standard deviation or a number of person, right?
Yeah.
And then you just solve it using that. So you have your um how to call it?
And
Constant.
then for the Z-score like sheet, do you get provided them or do you need to bring your own?
Z scores sheet, you wouldn't get asked a question about that on the tech free. If you
Ah,
would, it'll be your standard Z score. So you have your Z.
like 1995 or like 99.
You gotta memorize your 68, your 90, maybe not your 90. You have a question mark on 90, but definitely your 95 and 99.7.
Yeah.
Maybe not 90. 90 is a bit iffy because it's 1.64. 95 is at 2, and this is at 3. Wait, is that right?
Um, yeah, it should be. It's the imperial law or something, right?
Yeah, I'm just gonna set these scores.
It,
Uh,
I think it should be. But isn't 95 like specifically 1.96 or something?
1.96. Yeah, 1.96 also. Yeah, 1.96. My bad. 1.96, and then you have your 99.7, which is 3. I think so.
Yeah.
Yeah. What 99.7 is 1.3. Yeah. So yeah, and then your 90. I'm not sure about that. I do recall it being 1.64, 1.64 or something, but that's just it might not be correct. So don't take my word on the 90, but they wouldn't ask you for the 90 unless they give it to you.
Yeah.
You will need to calculate your Z score by calculator though, if you're on the tech able. Now, what confidence interval is essentially doing is just giving you a best estimate of where the actual mean lies.
Yeah.
And that's what they're doing. And let's say, right, for example, you have 40 trials, right? So your n equals 40. You
Yeah.
have your p-test, which is p gives you, let's say, 20%. Then, of course, if you want to get your confidence interval, you would find the standard deviation. They'll probably give you something along the lines of that, and you begin doing your confidence interval. So how will that look? Is that give me a minute.
Yeah. And then I think there was also like standard deviation versus standard error. Um
Mm-hmm.
and then like the definition of standard error. I'm kind of
Standard error is just your okay, even imagine your standard deviations from the center, right?
yeah.
Your standard errors from your two sides.
Oh, so one's measured from the middle
So
and then
imagine your standard deviations from the middle here, right? And this
yeah.
is your standard deviation. You get here, right? Standard
Yeah.
error is measuring from your two sides. It's also can be called marginal error. So Have you heard of margin of error before?
Yeah, margin of error. Yeah.
Yeah, your standard errors is very similar to that. Hopefully I didn't mislead you, standard error.
Yeah. So standard error would just be one side, and then standard deviation is both sides. What?
Yeah,
Yeah.
yes, by the looks of it. By the looks of it, yes.
So then margin of error would just be calculating the standard error on both sides of the,
Yeah.
yeah,
Yes.
yeah. Yeah. I think conceptually I've gotten it, but as
More questions?
actual like formulas, I might have to like revisit them once in a while.
Yeah.
It's-
So your standard, so while your standard deviation is technically like the measure of spread, your standard error is because your standard deviation, right, is based on your normal distribution, or what you hypothesize to be the normal distribution. Your standard error is your normal distribution. Well, your variance of the standard deviation, your normal distribution divided by the root of the number. That's what the standard error is.
Yeah. Yeah.
And this is what you'll be using,
Yeah.
if I do recall correctly, for confidence intervals.
Yeah. Um,
Does that make sense?
yeah. And then I think sometimes I don't know. I think it's just I didn't do enough questions, but some of the calculations it's like root of n 1 minus p on p, and then some of them the p is like p hat. Uh, like
I'll tell you what's the difference between p hat and p. P hat is your suspected, it's your population proportion.
yeah, and then p is
Suspected.
the raw population
Mm,
expect expected population with that trait
yes, and then p
is the actual.
is either the true, you can either denote the true, or you could just denote a percentage.
Yeah. So we're always trying to, I guess, find the p from p hat and the conditions given for p hat.
Not necessarily always, but you're generally, most of the time, yes, you would try to find p from p hat. You're trying to make, in the sense of confidence interval, you're trying to make a confidence interval for p, given that you know what p hat is, right?
Yeah. Yeah.
Because that's what you're trying to do. You're trying to find what's the actual true mean, in the sense that this is what the mean is. What's the true mean in terms of the population proportion, which is p hat that you are given.
Yeah.
Likewise, you could also reverse engineer it, and you could find. So if I know what the true mean is, right? Maybe it's a 30%. Give me a confidence interval in the sense that if I randomly picked 20, right? If I randomly picked 20 samples out of them, right? Give me a 95% confidence interval of the numbers that you'll be faulty. You could also reverse engineer it.
Yeah.
So in this sense, right? In this case, it would just be you have the actual number, right? 30%. And based off this actual number, you can create a confidence interval. Maybe around out of let's say 40, right? Your sentence is definitely going to be at 12.
Yeah.
30% of 40 is 12, right? And then your confidence interval for, let's say, the number of faults in 40. If you want to create a 95% confidence interval, let's say it goes from 8 to 16,
Yeah.
right? So it means that if you were given any test, right, and you're taking 40 samples out of it, the number of faulty samples, right, there's a 95% chance that it will lie between 8 and 16.
Yeah.
Does that make sense?
Yeah.
So
I
this
mean,
is the condition of, this is like, you know what the actual population proportion is, and then you're using it to find what might p hat be.
yeah.
What's the confidence interval for p hat? In this case, you would, well, I mean, one last thing, you would probably have to divide 8 over 40, and you have 16 over 40, you get the confidence interval at what, 20%, 20%, and to what's here, that's 40%. Does that make sense?
Yeah.
So that
Uh,
means you have a 95% chance that any 40 item object that you pick, there's 95% chance that 20% to 40% of those items are going to be faulty.
yeah. Yep.
Mhm.
Uh,
So that's your reverse engineer. And the other way, of course, right, is you know what your population proportion is. And based on that, you're trying to find out what the actual proportion is. And the question you're asking then would be, there's a 95% chance that the true mean is between these two numbers.
yeah. Yeah. That makes sense.
Hmm.
Yeah.
So that's what p hat and p is.
Yeah. Uh,
Is there any other questions? I mean, feel free. I still have to be here for half an hour.
and then with like back to the polynomial question that we did before, with
Yeah.
like those types of questions, is it generally like say what the question asks for, and then for example, if it's asking for the maximum like solutions, you would want one equation, like one like k value or k range that satisfies all the like requirements, right? Well, like how do you say it? Satisfies like all of the ones that says like k is greater than equal to zero, like it's greater than both
Satisfies
sides.
the
Satisfy.
satisfies the conditions that you want it to be.
Yeah,
Not all, but the conditions that you want it. It's
yeah,
very clear that you need to like distinguish between them. Because, as I said, right, if they were to make the question trickier, you would have one in which that you had to find all the. It might not be one single value, right? It might be, let's say, k is between. It might just be a chopped up bit. So, like, let's say it might end there, and it might go here, and it might end here, like this. You have a
yeah,
range of values in which that, if you were to write your answer, you would have to say k would be an element of negative infinity to a number, maybe say, let's say, -4. You also have to worry about closing brackets, full brackets, right? Or, right? Or you have your other -2 to 1, or 3 to 6, and lastly, 7 to infinity, like this. Then that is your full answer.
yeah,
It will be a range of values, and then they are chopped up in between. So that's,
yeah.
you
So
want to satisfy the conditions that you want that it needs to be in. Yes, that you want.
yeah. And
And
then
read the question, right? As I said before, methods is about reading the question.
yeah. Third one would be um
Any other questions you want to ask?
there's wait let me see, is your assertion no such values exist, explain why. um exactly two. Let me try solve this one question.
Sure. I mean, I'm here, so you can think of me as I'm just idle.
Yeah,
I'm idle here, available for the next half an hour.
all right.
So you could do the question there, and you have problems, then you just tell me, and then we can try to answer them all together.
Yeah, okay, be right back.
That's fine.
So for example, if it's like let me draw it. If it's like um would this like ever be would K ever be like would this ever be true? Like can K be like not how do you say it?
What do you mean, would this ever be true? Like those two things, I'm assuming they're x's, right?
Yep, X and then and then K. So would this like condition ever be like wait no wait let me think. So that
Always true?
this is a discriminant and I'm trying to because I have the other one so the other one is
Why do you have x as your discriminant? As discriminant, there shouldn't be any x's left. There can be anything else, but there can't be x's.
oh oh my God. Yep.
Does that make sense now?
Yep.
Your discriminant is your coefficient. It's not the x.
Um this one let me see. So that one. Okay.
That should
Yeah,
help.
there's no this thing. So there's no this thing. So would um
Would x minus k,
yeah
what?
would that always has a that would always have a solution, right? Like for this.
Yes.
Yeah. So
Why is it? Can you tell me? Can you have a guess of
um
why?
is that because X can always be zero?
Good. X can always be zero. No matter what k is, x can always be zero. Always a solution. Good
Yeah.
job.
Okay. Yeah. So yeah, okay, I get it. Because it's like another question, just like the one before where we're trying to find f of gx equals zero. But
Uh-huh.
this time one of the ones is the discriminant of one of the ones I got was like k squared plus 20, and in that case uh it would always be greater than zero, right? Because something
Yes.
squared is always positive, and then 20 is also positive. So positive
Yes.
plus positive would always be positive, and it's impossible to get the discriminant to be equal to zero or less than zero. So then that means that would have two solutions already. And because the question was asking for find the values of k that f of g of x equals zero has exactly two real solutions. If no such values exist, explain why. So
Mm-hmm.
then I would just say if the other one definitely like always has two solutions and and for this one x equals zero would always be a root.
Mm-hmm.
So then there would always be at least three
Three solutions.
solutions, and therefore k no such value exists.
For k. Good.
Yeah, nice. And then for the other one, it's asking for find the values of k such that this thing has exactly four real solutions. So then
Mm-hmm.
if k squared plus 20 is always greater than like is always greater than zero, so that means it's always two solutions, and then k would just be all real numbers, right?
Yes, for all real numbers.
Yeah, and then so that means for the other one, if you're taking the discriminant, and then after you get the discriminant, it would just be that, right? It would just be that inequality, because all real numbers, it kind of satisfies like all of the range. So it would just have
Yes.
to be the one you get from the other one.
Yes. Your crucial idea here is just your if you want to check the number of roots, always check the discriminant. That's just the main thing.
Yeah.
For quadratics at least. And in the sense of composite function, right? You're gonna need quadratics. They're most likely gonna question you about quadratics and even cubic functions. You could take a factor out and you'll still be left with quadratic.
Yeah.
So discriminant does matter and it's quite important.
And k squared greater than zero. Um, But okay, so if k times k min oh sorry, x times x minus k is the was like one of the equations. Um,
Uh-huh.
if we find the discriminant of that, it would just be k squared, right? It would just be k squared.
It would just be k squared. No, not just k squared.
It wouldn't be just k squared minus
X
4.
squared minus kx. Now tell me, what's the thing in front of the x squared? It's 1.
But the c value is 0, so wouldn't
Oh,
that
true. Yeah, good. Good call. Good call. I forgot about that. And I forgot the c value that existed. My
so
bad. So yeah, it would just be k squared. Yes.
k squared? And then since it's four solutions, would k just equal to all real numbers?
Uh, no.
No.
Wait. How many other roots do you have
Uh,
already?
the other one is all real numbers, right? Because k squared plus 20 is always greater than 0.
Yes.
So then k squared, if k squared is greater than,
And you
so,
also have a equation that you have
oh, I
x equals
mean,
0 as one of your roots. So if you were to get, so that gives you 3 roots. So you were to have 4 roots, you'd need that thing to be just bigger than, you just bigger or equals to 0. And that'll be enough. If that's what you mean.
yeah. So the question is just asking find the values of k such that f of gx is equal to 0 has exactly four real solutions.
So what's fx and what's gx?
Fx is x squared minus 7x plus 6.
Mm-hmm. X squared minus 7x plus 6. Yep. And last but not least,
And
we
then
have gx.
gx is x squared minus kx plus 1.
Okay. And it's find 4 solutions, right?
Yep.
So it's f of gx, right?
F of gx. Yep.
Now, my tip for you is that what do you do first? Tell me your thought process.
Factorize it because you're trying to make that equal to 0.
Factorize which one? Top or
The
bottom?
fx.
Good. And you're left with x
Uh,
minus 6, x minus 1.
yep. And
Good.
then because, and then plug in the gx for the fx, the x value in fx.
Good. You get x
With then
squared
you get
minus
x squared
kx
minus kx,
minus 7.
uh minus
6, minus 5, my bad.
5. Yep.
Yep. And then you have x squared minus kx.
Yep.
Yeah.
Yep.
This one, you don't need to talk about it. This one, it's, well, in this case, this one, it's k squared plus 25.
Plus
And this
25.
one, this would be k squared, right? Now you want 4 solutions. So this one will always give you 2 no matter what. So we could just ignore
Yep.
it, right? Ignore it.
Yeah.
You already, you will need 2 solutions here then,
Yeah. And
or
then
4.
x squared can be anything but 0, right? Because 0 wouldn't be greater than 0.
Huh?
Like k can be anything but 0, right? Because
Yes, k
0
can be anything
squared.
but 0.
Yeah. So then the answer to this question would just be k is equal to all real but 0.
Yes,
Yep. All real but 0.
yes.
Let me check the answers. Um, 3, 4 solutions. Let's see. Page 24. Which page? 24. Okay. Yep, that's the answer. K is yep.
Mm,
Yeah.
So generally, it's not that hard.
Yeah. As long as you get the logic correct.
Yes.
Yeah. And then the other one is to just check if there's multiple cases. For example, if you have yeah, if you have something that has a degree of like more than two, say, and then like find the values of k where f of gx equals 0 has like one solution, then you have to consider for each of the roots.
Yes. Not for this question, because this question is a little bit easier,
Yeah,
but
yeah,
for the previous question, yes, if you because the previous question, that one, if you were to want only one solution, that would require a little bit of uh pinning out those little intervals by yourselves.
yeah.
Yes, that's pretty much
Uh,
it.
yeah. And then for this one, it would be true because it's a quadratic and another quadratic, so that's like degree of four in total, and
Three
that's
or
you
four.
can only get maximum of four solutions.
Yes, degree of four, maximum four. Yes.
Yep.
It even works for complex numbers. The number of degrees is the number of solutions you're gonna get.
Yep.
Yeah, I'm pretty sure it's gonna start complex number. You're doing special, right?
Yeah, special.
You're gonna start complex numbers soon.
Yeah, I think so. Because right now at school, I think we're learning about unit vectors.
What subjects are you doing, by the way?
I'm doing English
Physics?
mainstream. Uh, I actually do Comp Phys, which is like a JMSS like special year 11 like subject that combines spec and physics. But
Yeah, to be fair, they're similar, yeah.
yeah, and but like I'm not sure if they're like teaching it well because everything they're just skipping ahead, and then with the content itself it hasn't really merged yet. So it's kind of like in one lesson we only learn about physics, and then the other one we only learn about spec. So hopefully like later on we can like get to some more like combination projects.
They did cut the special. Do you guys have any study design, or are you still using the 2023 one?
Um, I think we're still using the old one.
Ah,
Yeah.
they cut they cut the physics content, I bet. I tell you, the only thing that's left about special physics is kinematics.
Oh, damn.
Kinematics.
Kinematics.
Yes, kinematics is interesting. It's actually quite simple. You just have a few velocity things and then add a little bit derivatives. So that would be the most difficult thing you have in kinematics, which are derivatives. Double derivatives for accelerations, etc.
Yeah. Derivative
Yes,
of acceleration is jerk, right? But I don't think we
you're not going to cover that.
yeah, okay, yeah.
It's mainly they give you acceleration, and you anti-diff it, anti-diff it again, and then to give your speed, etc. With a lot of criteria, and also you have to decide, oh, am I anti-diff it now? I'm going to use some of the kinematics formula, such as A equals to blah blah blah.
Yeah. Um let me think. It's always the displacement time graph, and then you derive that is the velocity time graph, right? Mhm.
Derive it again, and you get
Yeah.
acceleration time graph.
Acceleration. And then reverse
Speed
reverse
time, you derive it, get what?
speed time.
Yeah, you derive it, you get what?
Speed. Speed is scalar. So
hmm
uh um what do you get?
Well, I think for speed, when you derive it, you're technically it's similar to acceleration, but it's not quite accelerations. So I think I was supposed to ask the anti-diff, but the anti-diff of speed, what's that? Speed time graph. So you have
Uh would
yeah,
that be position? Would that be position?
there's another word for it, a better word.
Uh
Starts with D.
disposition.
Very close, not disposition. This what
Dis
place?
displacement.
There you go, displacement time. Displacement time and the diff of speed. Uh,
Speed. Speed. Is
Diff
wouldn't
diff
you use velocity though? Because like speed is scalar.
speed scale. I know, but you would you? Nah, the thing is, right? Nah, I mean that the differentiation speed. So your velocity differentiation is acceleration, right? But then your differentiation of speed. I'm still trying to think of what that is. I don't think there is a really derivative of speed. Wait, is it still velocity?
I think it would be velocity. Because
No, it'll be velocity.
wouldn't you want all the units to like remain in vector quantities?
True, true. Yeah, it will be velocity.
Yeah. And then I think it's just a little bit confusing at the start because I keep kind of visualizing displacement wrong because displacement time graph it's really just the exact location from the origin or not origin but like the original position like since he started the time and it
Yeah.
wouldn't be like it's not like for example how would you say it? You don't take account for the line itself. So,
Yes. So you could have
when,
the idea of you traveled, right? You traveled this much. Let's say if you look at it, you traveled this much, right?
yeah.
But then your actual displacement would only be this. You
So,
or just only be that little bit.
derivative of position would be the velocity.
Yeah.
Yeah. Okay, nice. Uh, I think before
Oh,
before we finish, there's just one more question, I think.
sure, no problem.
Uh, it's got something to do with like fluid dynamics. So, I think with just like the general, it's in the it's in the gauge pressure like unit. So,
Mm-hmm.
for example, if say water is entering a pipe from the very bottom of a building at a certain
Mm-hmm.
at a certain pressure, and
Mm-hmm.
it might say that from that point to the first floor is 6 meters, and it's asking whether the water would flow from the faucet in the like at uh
That's spilling out the water,
yeah
right?
at level 1, yeah.
Hmm. Interesting. So it depends on how big
That's
the faucet. Where's the faucet located?
it's in level 1, so 6 meters above the original pressure when the pressure like pushes the water up. Like the water starts from 6 meters below level 1, and then
Mm-hmm.
at that point there's a certain pressure.
Uh, and then it starts to gradually fill up
Yeah. And
until
then
you
I
get to
think
level one.
yeah, I think it's just the general uh like kind of conceptual or like I can't really visualize the gauge pressure because
Of
it's yeah.
course, right? It's different. So oh, okay. How am I gonna supposed to explain this? You can think of the idea is that because the water faucet, it doesn't begin with flow. It wasn't filled with water to begin with, right? And it's asking for the faucet's pressure, right?
Yeah.
It doesn't begin that to be filled with water. So when the water comes to the faucet, of course, there's going to be a different pressure inside the faucet, and it's going to be a different pressure outside the faucet.
Yeah.
So that makes sense. So if you think about it, right, water pressure works like this. It's technically the weight of something that's being it's the weight of the water on top of it, right? So imagine you have your faucet here. Now, of course, this faucet itself is not going to be completely filled with water, right? It's empty per se before any water comes in from here.
Yeah.
And even if it's open, right? For example, it fills up and still open. the water coming from the faucet is flowing, it's going to have a different pressure to the waters here.
Yeah.
Does that make sense? Because this water, before it's when it builds up, I mean, of course, when you get at the bottom of the water, your pressure is going to be higher and it's going to be gradually decreased as you go up. The water pressure, I mean, technically. Not maybe not the actual pressure, I would just tell you. But the pressure inside here is definitely going to be different because one thing, the water's flowing or it used to be flowing, or second, if the faucet's closed, once it reaches here, then of course it's going to be air, right? And if it's going to be air, and if you think about it as have you created air bubbles beneath a boat before?
Yep.
Even if something sinks to the bottom of the ocean, you can have air bubbles trapped inside, and that's how it works, right? It's a different pressure under there.
Yeah.
So you can think of it like that. It's just a different pressure under there. And then what you want to do in physics is you want to calculate what those pressures are.
Yeah. Yeah.
And there should be formulas for them.
Yeah. I think, yeah. I'm pretty sure static pressure, like for the like Bernoulli's principle, there's like three bits. There's like a static pressure, which is rho GH, I think.
Mm-hmm.
And then the
Yeah, GH. Yeah, rho GH. This thing, right? Oh wait, let me draw rho and a GH. This one.
yeah, rho GH, and then rho would be the density of the fluid itself. So that's
I
water,
see.
which is 1,000 kilograms per meter cubed.
I think it's 0.997, but we can ignore it.
Yeah.
We can ignore it. I mean, I remember in university physics, they approximate the pi as 3.
If
According to some of my friends, they approximate the pi using 3. Yes.
would you say this like the fluid bit is like one of the hardest topics for physics 3-4?
According to my friends that it was quite, but then I feel like as long as you understand for physics and for many maths and chemistry as well, you had to be curious and you had to ask why does this happen? And once you find out and you keep curiosity and once you find out you would understand it. It's much important for you to actually understand the logic behind it than to actually do it. Does that make sense?
Yeah.
So for
So
maths, physics, chemistry, you understand the logic behind it, you get the question. So
yeah.
it's not necessarily about hard, it's about whether you understand the logic behind it.
Mhm.
Whether whether it's like you're having difficulties for understanding the logic behind it, that's where you justify whether it's hard or easy. But I mean most people don't try. Most people just I see this formula, I'm gonna use it.
Yeah.
That's generally not what you want for a lot of your maths or STEM subjects. You want to know the actual logical reasoning behind it. For example, I remember in in Sesh, I think because we were curious about how anti-diff works, then we went on and we discovered how anti-differentiation actually works. Why does integrating a function gives us the area beneath it?
Yeah.
So
Is it just
and yeah,
is it just like the fx and dx thing, or is it like more logical than that?
f, x, dx, and then you include something with the idea of
Yeah.
yeah, yeah, it includes the idea of how anti-diff came to be.
Yeah.
How anti-diff, why are you adding a power two on top of that, etc.
Yeah. And then in Spesh, would there be any topics that would require you to use the disk method? Because I just learned that today from one of my friends, and I think it was pretty interesting.
What's
So
a diff? What do you
disk
mean by
method.
disk?
So basically, I think it's like, oh wow, my drawing. So for example, it could be a thingy like this. Say that's fx, and
Mm-hmm.
then um, this point is A, or like
Mm-hmm.
origin is A, and then you want to diff it to this point, which is like B. And then I think the question was, uh, if we use this, if this was half, like the area under here, the integral like here is
Mm-hmm.
um okay, I don't know how to explain it, but if you visualize it kind of like this, but as a volume, as like a 3D object, where the thing you just found was like this bit, you know? Like if
Yeah.
if it was like a cone thing, if it was like a cone shaped thing. So
Yeah.
around the y-axis, you rotate it 350 degrees, and then the volume of the object that creates, you would use the disk method. So I think it was like the same formula as how you would find the volume of a cylinder, which is
Mm-hmm.
pi r squared h. But
Mm-hmm.
then we know that these little segments are dx, right? But then each of those little segments would kind of be like a disk. Um,
You will learn that in Spec. It is what you call finding the area or volume of a graph when it's being rotated around either the x-axis or the y-axis.
with the y-axis, you can just make it inverse, right? Can you? And then
Uh, yes, you could just make it inverse. You could just chuck it
yeah,
away. For the x-axis, right, you want to find the volume of it around the thing. That's also how the volume of a circle came to be,
yeah.
of a sphere. If you take a look at it, what do you see? Remember, what does a sphere look like? What is the function part of the sphere? Let me draw it out for you, right? We all know that the volume for a sphere be equals to what? 4 over 3 pi wait. You said 4 over 3 pi r cubed, right?
Yeah.
Yeah, so we all know that's the thing. Now let's take a look at how it went to be, right? We know for a sphere, our function is supposed to be x squared plus y squared, right? Equals to 1. Now we're only limiting in this part to technically the x-axis, right? We want to rotate around the x-axis. Here we
Yeah.
go. And now we have our thing, which is if we want to take a look at y squared would be 1 minus x squared.
And then you root that, which is y equals root 1 minus
Root
x.
it, double it. Root it, you get one side or you could double it. So you get y equals to root 1 minus x squared. You can, and then you start doing the diff, right? You could double it, right? You get so you anti-diff it, you get the volume, which is you get thing, but you want to multiply it by 2 pi because each of them is a circumference of this, right?
Yeah.
Circumference. Get the circumference and you're adding all the circumference together, right? No, the area, you're adding all the
Area,
area,
yeah,
and
the
each
area
of the
is
radius is r, right?
r squared, yeah.
R is y in this case.
Yeah.
So you get what? So you get pi. I want to add pi r squared
Pi
over from 0 to 1, right? Of course.
0 to 1, or would that be negative 1 to?
Well, you could go negative 1 to 1, it doesn't really matter, but
Or you could like just double that, right?
because we don't have the yes, I'm just trying to find this part here, right?
Yeah.
And then we can just double that at the end.
Yeah.
Now that would be dx, right?
And then
I
since
know what r, right? What r is.
r is would just be root of 1 minus x squared. So if
So
you
if you
do
r
that,
squared that, you'd
you
still get
can
y squared, right? Y squared is 1 minus x squared. Now,
yeah.
using that, I could just change that to negative 1, and I have negative 1 to 1, and I have pi times 1 minus x squared
Yeah.
dx. And then if you solve that, you'd get your answer as being negative 1 to 1, you have pi,
Right. And
which
then
then pi dx then minus negative 1 to 1 minus
the,
x squared
the,
dx,
the,
right?
the pi.
Pi
But
x squared dx.
do we have
But
to?
this cancels out, right? This doesn't exist.
Yeah, that's just x, right? You just have yeah.
So again, negative pi from negative 1 to 1, x squared dx, and then if you decide to do that, you get negative pi, I think it was if you anti-diff x squared, you get 103. I might have been missing something, but oh well. I might have missed something, but oh well. So x3 from 1 to negative 1. And you get let me think where I went wrong, but I'll have negative pi on 3, and I'll have negative 1. I might have done one of the negative
But
negative pi on 3 again. Yeah. So I'll have negative pi, which equals to
wouldn't
negative
the one be
pi.
x? Wouldn't like when you take the thingy out, wouldn't it be pi times integral of -1 to 1 of 1 dx, which would become x? So it would be x
Oh, you have
minus.
negative 1 to 1. They cancel.
Oh,
Wait, no, you double it. My bad. They don't cancel.
yep. So
Yeah,
you
that's my bad. So you still get double. Yeah, you get double. Yeah, that's my bad. Ignore this for now. Ignore this. Pretend that didn't happen. You get negative 1 to 1 pi dx, and then that's still minus pi, and I have x squared dx. Okay, good. That looks so much better. And now you would have I think that would give me pi plus pi. So
right,
that would be 2 pi.
yeah.
2 pi, then minus you have pi, and then you keep pi, and then you have 1 on 3 x cubed from 1 to negative 1. So you get 2 pi minus pi on 3, and then you have 1 plus 2, which you get 4 pi on 3, which makes sense, right?
Yeah.
Because your radius is 1 in this case. And that's how the area of the circle, the volume of the circle came to be. A volume of the sphere. You're just integrating the area over the radius.
Yeah. But for this specific example of -1 to 1, would that like not be the best way to kind of visualize it as
You could
one?
go from R to R. You
Because
could go
like
from negative R to R.
because
That
like
also works.
yeah, I mean because like I squared I mean 1 squared 1 to the power of anything would just still be 1. So maybe if
Yeah,
we
but you
take
could go, but
negative
you could
function.
replace. No, it doesn't really matter because you could replace it with negative R. You can replace it with negative R. It will be the same thing.
Yeah.
You could replace it with negative R to R, and the only thing that would change would be from here, rather than being 2 pi, you would get what? You get R2 R squared pi, right?
Yeah.
Or in the other case, you get 2 pi R squared.
Yeah.
And then from here, you'd get, well, not pi R squared, pi cubed. My bad.
Yeah. So yeah. Well, yeah, like what I'm trying to say was that like the 4 pi on 3, because like it doesn't have the because like but the one cube just like kind of you don't have to write it. So for some people it
Yeah,
might
I
be
understand what you mean. I understand
yeah,
what you mean. Yeah.
yeah.
Yeah, I get what you mean
Maybe
in this
generally, yeah, I get it.
sense.
Yeah.
Yeah, so it's just that, and in this case, right, because you had to change this from R again. It's not 1, it's R. If you see what I'm doing here,
Yeah.
it'll be from R to R. So the equation will be from negative R to R, and you have pi times R minus x squared dx. Looks like this.
Yeah. And then once you solve it, it would just be
4 and 3, pi R cubed.
yeah. Oh,
It was a fun fact. And this is what you learn in 3/4 batch, not now.
yeah. I feel like it'd be pretty fun. I think
It is fun, this part. You would
yeah,
also find the
quantum physics.
arc length of the of the equation of the graph
Oh, the length.
of a graph.
So
You
like
would also find that.
how would
So I'll give
like
you an example,
is
right?
it just like the for example
So you imagine you have a graph like this. It's
and then
asking you what's the actual length from this point to that point.
oh
There's a formula for it. It's actually
like
quite pretty.
the line itself, like counting the line or
Yes,
just like the straight line distance, because that
the line itself, the
yeah, okay,
curved line itself, the distance of that,
yeah,
the length of the line.
yeah. So
It is quite interesting, and you would enjoy it if you're a STEM kid. You would enjoy it. If you're not a STEM kid, you'll be fascinated and say, "I would. I. It's interesting, but I don't want to touch it again."
yeah,
Yes,
yeah,
that's what you would cover, and that's pretty much it. And then you also have like some others, maybe like you have some interesting anti-diffs between trigonometric functions, like you get introduction to your hyperbolic functions.
Yeah.
You know what hyperbolic is?
Hyperbolic is hyperbola.
No. Wait, is it
Hyperbola.
called hyperbolic? Wait, let me give me a moment. Pencil. Is it called hyperbolic? Hyperbolic functions.
Nope.
Yeah, nah, they are called hyperbolic functions.
Yep.
They're fun. So I'll
Yep.
tell you what they are they. You have your first hyperbolic function. You have shine,
Shine.
posh,
Kosh.
and tan.
Ton.
Now, what is shine? It is e of x, wait, plus e of negative x on 2. Yeah, this is e of x minus e of negative x on 2. All the other way around. They're
Hmm.
fun. And why are they important? Because I will tell you one thing. I think the antidiff of 1 minus x or x squared, one of them, dx. I think that should be tan.
Yeah. Uh, if
Fun.
the wait Sine if like tan h, if you were to find tan hx, you can't just find it through sine hx over cosine hx, right? Because wouldn't the h like cancel out?
They won't cancel out. They're the other way around. So I might have done it around. So this would be a minus and this would be a plus. It is just sine x on cos x, but they won't cancel out. Guess why?
Why?
Yeah, because this is a plus, this is a minus. So you have e of x minus e of negative x, right?
Yeah.
Over e
Yeah.
of x plus
Fine.
e of negative x.
Yeah.
Doesn't cancel out.
Ah, that's crazy.
Have fun. You also have trigonometric, hyperbolic identities that comes with it. The similar reasoning, you have trigonometric identities, right? You have sine squared x plus cos squared x equal to 1, right?
There's also gonna be like U subs and stuff, right? As well.
Yes, U sub's the fun part. In
U
this
sub
case, in the terms of
ups.
shine and cosh, you have cosh squared of x minus shine squared of x equal to 1. So from this, you can have a very interesting relationship is that if you equate these two, you get sine squared x plus cos squared x equals to cosh squared x minus
What is
shine
the
squared
what does
x.
the H represent?
It just means it's hyperbolic function.
Ah, okay.
That's why it's h, right? Hyperbolic.
Yeah. Nice. Nice, nice, nice.
Yep. And you have the cosec, cotan, and cotan, right? No, no, no. Your yeah,
Yeah, those ones. But
those ones, right? You also have those. You have also have this. You have
uh,
hyperbolic, which is they
that
have very weird names at this point.
I think before that I need to just get the conversions right first.
Yes, you have a very, very interesting name. This is cosecant.
Cosec. Okay. Yeah.
Cosecant. Yeah.
Cosecant. That's for wait, let me think.
Cosecant is just 1 divided by sine.
Yeah, one
Uh,
divided by sine, and then secant is one divided by cosine, and then tangent would just be that. But then when because like you can find everything in terms of sine x and cosine x, right? You can find everything in terms of them, whether it's like differentiation or just pure conversion. You can find everything just using those two, right?
what do you mean by find everything in terms of those two in terms of
Like for
trigonometric functions?
for example, if you're trying to find the derivative of like secant x,
Yeah,
you
you could
can
just use them.
yeah,
You could
you
just
can
use sine
use
cos.
just yeah,
That's completely fine.
yeah.
All right. So you also have and then yeah, that's pretty much all you have to worry about, honestly, because that's about as far they would go. Anything further from that is university. Although I do say, right, what are you planning on for your career, just by the way?
Um Right now, I think,
Med?
not really, not med, med's
Okay, good.
stressful. Either like I'd say aeronautical engineering, so
Hmm.
like planes and stuff, or like maybe like something to do with sports science.
Okay, so I think I know I know what you're going with. So
But
if you're going
probably
for aeronautical engineer, I recommend you could try to do a subject or two or uni maths and then
yeah. I'd say
do you do
I'm
chemistry?
yeah, chemistry, yeah.
Scrap chemistry.
Scrap chemistry.
You can consider if it's not a prerequisite for aeronautical engineering, scrap chemistry, and go university maths.
Yeah. But
So because the thing is
wouldn't
with university maths, you can do it at John Monash. It's available there.
yeah, but like cutting off wouldn't that be too risky? Because like what if I change my mind? But like chemistry is like one of, if not the
That's why
biggest
you can still do
field.
Chem 1 too. It's only up to next year. And if you haven't decided what you're going to do next year as your career, then if you made it a halfway check, sure. What other subjects are you doing? I'm thinking of is there any better choices to cut off?
Special
Physics, methods, spec, and English mainstream. These four are compulsory. You also have chemistry, and what's your last one?
chemistry and Chinese.
Chinese. Nah, I guess if you want to cut off, it's only chemistry, but
Yeah. I
it's your
was
choice. It's your choice after all, right? If you really don't, if you're, we'll see at the end of this year because you have until the end of this year to apply. Do you recall?
yeah. Because like would you say if you're like not ready to kind of not like not ready, but like if you don't want to commit that much to Chinese, should you do it at all? Because like I'm doing SLA and I'm actually quite disadvantaged because like I'm only how do you say like not passing the bar for SL by like a year or two.
I did SL. I did SLA. My bad. I haven't even gone to primary school in China. I did SLA.
Oh, was it did did it go well?
Uh, let's just say it wasn't the best, but
It was all right. Like would you prefer that over uni maths?
the thing is, I would have preferred uni maths over chem. Okay, so the thing is, right, Chinese SLA, I only got a 34. It's scaled to 42, and it's still in my top four because all my rest was very high, and
Yeah.
I got a decent stuff out of that. But if my SLA went better, then I could have gotten quite
Yeah.
higher, quite
Yeah.
significantly higher. But yeah, it is what it is. It
Um,
only gave me a scale of 42 at the end.
yeah. So just stick with the current
Stick
schedule.
with the current schedule.
Believe,
Think of it.
believe
Still,
in
it still scales by 8.
Yeah.
That into
Yeah.
consideration.
Okay.
Like you get a 34, you get a 42. And then if your scores are like mine, which is I think it was you'll
The
probably do better than me. I got 30, I got 43 in methods, I got 44 in spec, and I got 39 in mainstream. You'll probably do better than me.
like the thing is I don't like I feel like I don't need too high. I just don't want something like low enough that I might be upset about. Like anything I feel like
True.
that's kind of like good enough, which I'd say would be like
Yeah, so you're completely fine. I mean,
95, I'd say, or above. I think I would be pretty okay with.
Dura has 195, then just go with whatever you want, because at that point you don't need to really worry about it. Chinese SLA, get a 34, like what I did, it should be all right. I was hoping for
Yeah.
higher. I was definitely putting much effort for it. I think my study scores, my maths were very high. My maths was relatively high, and all the rest were like around 40,
Yeah,
aside from Chinese SLA.
that's pretty good.
And
40.
chemistry was my seventh subject, so because I was forced to do it, I regretted it
Yeah,
because
because you did like all those stuff on top of
you
what
maths.
yeah, uni maths.
Well, the thing is, right, I did three
You
subjects
get-
in year 11.
Was
So
it like much helpful towards like your engineering degree?
I'm not engineering, but it was helpful to my degree.
Oh, not engineering? But oh, yeah. Was
I'm
it commerce?
actuarial.
Was it commerce or something?
Yes, actuarial commerce.
Commerce.
So
Yeah.
the maths part of commerce.
Yeah.
So yeah, it was helpful in the sense that it saved me $1,000 worth of tuition fee and maybe a year paying in first year, but
Yeah.
it really depends, right? Because I remember if your results for UniMaths doesn't count towards your WAM, doesn't count towards your university average.
Yeah. Okay. Yeah. But it, it
And
it does count towards your ATAR, right?
it's gonna be a fifth or sixth. So that's why I said, right, if you're like only do this if you're 100% sure you're not gonna pursue anything with chemistry, then scrap chemistry, take UniMaths, and then because UniMaths you only need to you pretty much only need to pass,
But
and you could save yourself. You can dedicate way more time into your English.
yeah, that makes sense. But with that, is there a lot of workload or is uni math just kind of like a breeze? But like you actually learn
You
something
want to pass? It's
quite a
just
bit.
like probably because you're doing special.
Yeah,
It's just an extension of special.
yeah.
Linear algebra is gonna be a little bit pain, but it's just an extension of special. And uh, yeah, calculus 2 is gonna be extension of special, and you might actually help with special, but linear algebra is the only one that I would say iffy about because it's a little bit different from what you would learn. But that's the only that's the only downside I would say
Yeah.
because you only need to pass in Unimass because I would just tell you this: pass will give you a 3, aggregate of 3, which means a 30, which means that's 50%. 60% gives you a 3.5, 70% gives you a 4, 80% gives you a 4.5, and 90% plus gives you a 5.
Nice.
Yes. Yeah, so
But
it really depends on, right? I mean, I for you, right? Because you don't need to really necessarily go for that very high score. I'd say still take chemistry. It broadens your choices.
yeah, yeah, yeah.
For me, it was pretty much because I know I'm probably I'm stuck with maths. I got my university degree set when I was in year 11. I know what I was doing, and I know it's going to be maths. So I chose to do three subjects in year 11, hoping I get year 12 off a little bit easy. But no, my mother decided to make me take a seventh subject.
So,
Oh well, it was all right. Like aside from Chinese SLA, the economics and methods both got a 40 plus. So economics I got 40, and methods I got 43. So.
yeah. Yes.
And SLA was just that. It was just down the hole. But don't worry about it.
I think, yeah, just
And despite
um
SLA being so low, I still got a decent ATAR.
yeah. So I guess just study, lock in when you need to lock in, and then when you can lock out, just enjoy the
Yeah,
high school years.
because you don't want to pressure yourself too hard. I mean, of
Yeah.
course, if
I
you're going
mean
for
it's
med,
like
then ignore what I said. But
yeah, it's like I guess it's up to fate. Yeah.
yeah,
Just do
you
your
you
best.
only get one thing. You only get to live high school once in your life. Enjoy
Yeah.
it while you can.
Yeah,
Have a
that's
balance.
so
Decide, decide what's best for you, and just you know what you know what you're aiming for, and you know you're probably most likely going to get it. Then why don't you just like study? Of course, is one thing, but making that balance, enjoying life while you can, is
fun.
quite important.
Yeah, for sure. For sure.
Make some memories. Make some memories that will last.
For sure.
For me, year 12 was so much better. It helped my mental health so well because despite my mother forcing me to do chemistry, I was ha, like hell, I'm gonna put in effort. I went into a SAC unstudied, and surprisingly, I got average score,
Damn.
which says something about my cohort's ability in chemistry. But
Which school did you go?
Nozzle.
Oh, Nassau.
We have the good kids, which are very good at chemistry, and we just have the other kids just there.
Nassau.
Which
It's not. Would you say? Wait, Nassau. So does that mean you did the test for like Melbourne High as well?
yeah, I did the test for Melbourne High.
Was Nassau just closer or?
I mean, both were the same. It's just that Nozzle offered me first round. I just went, oh, okay. I got three superiors and two above averages, and I still and they didn't choose me for Melbourne High, so I was like, okay, I'm not gonna be bothered. I'm
Yeah.
not gonna be bothered, so I just gonna go straight to Nozzle. I mean, it was decent as well. It's pretty good.
Decent. Would you say like most of the Nassau kids like are they I don't know how to put this in a nice way, but like kind of uh 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 like some of them. I wouldn't say definitely not all of them, but like some of them are kind of uh how would you say kind of leftovers in a sense for Melbourne High. Maybe because like some
Some,
of the people
some,
from my
but
school
a lot of people I know they chose Nozzle as first preference because Melbourne High was just way too far in
way
South
too
Yarra.
far. Yeah, yeah,
Like,
makes
and
sense.
I'll just tell you this, right? Because there's a lot of immigrants that came to Victoria, and majority of them could only mostly afford housing down at the more regional, right?
Nassau is more.
Like not always considered a little bit regional. You because they Berwick has a new building. Berwick also has a Haileybury. Berwick has like around Berwick. There's a lot of people who went in, and generally, I mean, immigrants, right? You have the smart. You have smart agents, and they're just like, nah, they're not gonna go for Melbourne High 'cause it's just too much of a thing. And to be
Yeah.
fair, this year's Nozzle's ranking was pretty high.
Yeah. I
If
I'd
I do
say
recall,
yeah. I'd say for JMSS it's just the English. If it wasn't for English, I think with if we're just taking account for just the STEM subjects, I think we'd be top 10 because like a lot of the students are like really good at math.
yeah, so far it's Melbourne High, McRob, and Nozzle.
But
But
other
then,
than yeah,
but then that was like general overall, and we're taking a look at VCE results, and I'm pretty sure it's
yeah,
yeah, it goes Ballarat, McRobertson, then Nozzle, then Haileybury. Melbourne High is actually lower than Haileybury, which is fun. Not lower than Nozzle, which is funny in a sense.
yeah. Yeah, because I know that JMSS is definitely mostly kind of leftovers for the selective entrance exam. Like for example, I personally I didn't do the best in that test, but then for
It's fine.
JMSS I got like four superiors and one like above average. So
Yeah, that's fine. It's like it's more of a just give it a try. Honestly, I know, Grace, the one that I told you about, she applied straight for GMS that she didn't even bother applying for Melbourne High or
Rob.
McRobertson.
There's
Yes,
only like one person I know that comes from like uh like one of those schools, which is like McRob, and it's really surprising because like McRob is really high in the rankings. I'm not sure why they came.
it's really just like because I have my sister went to McRob, right? And she told Grace that don't go to McRob because it's just not suited for her personality. She would thrive much better in
I'd
John
say,
Monash, where there's a much better social life.
yeah, I'd say so,
Because
probably.
you guys live right near goddamn university. You guys have pretty much half a uni life.
Yeah.
Yes, so
There's
and it
definitely,
feels her personality.
there's definitely a lot more like more to studying, even though there's like heaps of like STEM stuff and like academic related stuff. There's also a
Hmm.
heap of like other opportunities, which is definitely better for people that want to enjoy instead of just locking in.
Yeah, it's not really enjoyment instead of lucky. Some people just they need a mix. You can't really lock in. For me personally, I was consider I locked in hard for year 11, and then for year 12 I kind of just went on the thing with because I was so familiar with the content and I was also doing uni math. So I was doing special tests while playing the game. I could do two things at once. For my methods, it became at the when it was nearing up to the test, like about 2, 3 months before the test. I've already done like around 50, 60 sets of past method paper. And at that point, when I start a new paper, I go on my computer, I play a game, and I have a game of whatever chess it was, and I have my test, and I do both at the same time because it was just the idea of it's gone to the point in the sense that I know what I need to do. My goal of doing more tests is just to refine these and also look at perhaps possible new interesting questions.
Mm.
Yeah, so it's just really depends on your own habit, and that's what you had to find out in very soon. You had to find your own habit of studying and what makes things easier for you.
Yeah,
Like soon, you need to find that soon. Otherwise, your year 11 would hurt.
yeah.
Yes, and then yes, and there's a thing called burning out, right? You heard of it?
Yep, definitely. I've experienced that.
Yes.
Definitely.
So having a mix, making a sustained, it's much better than just burning out.
Yeah, definitely. I think uh I definitely experienced that, especially during the holidays, because I was trying to like really lock in and like lock in for every single subject, and I did that for about like 3 days, and then like on the fourth morning, I just didn't want to wake up. I didn't want to face like any books, any types of questions. So like I think for the following week, and then for the like next week, I kind of tried like a combination of like going to the Australian Open or like doing sports and like swimming, tennis or stuff. And then for the second half or like the other half of the day, I would, read some books and then try to complete the stuff like not like little, but like each section at a time. So
Yeah,
I feel like that was a lot better for productivity
it's
and
much more motivating to you when you actually do things out of voluntarily
yeah.
than you're forcing yourself to do it. So,
Yeah, for
all
sure.
right, anyways, it's been a while. I need to go eat. I'm a bit hungry
Yeah,
now. We'll
okay.
see you
Yeah.
next week.
See you next week. Thank you
If
very
you have
much.
any other questions, feel free to ask though.
Yeah.
See ya. Bye.